All right, AP Physics, here's your first little review of the most missed questions for your multiple choice problems on AP Classroom. And your first one's over your kinematics. So I'm going to go through the problems that the majority of you missed, those who completed that. And if you have other questions besides those, feel free to email me, and I'd be glad to answer them. So here's the most missed one on the kinematics. An airplane travels horizontally at a constant velocity v. An object is dropped from the plane, and 1 second later, another object is dropped from the plane. If air resistance is negligible, what happens to the vertical distance between the two objects while they are both falling? The correct answer is B, or A, it increases. And most of you who got this wrong chose C, it remains the same. And I can understand why, because you think that they're accelerating at the same rate, and they are accelerating at the same rate. And if they have the same acceleration, you might attribute that to being the same distance between the two, but that's not the case. And here's why. I want to walk you through this conceptually. If the black ball is the ball that we drop first, and the red ball is the one that we drop 1 second later, we're just going to look at their motions over time here. And the first thing I want to point out is your horizontal velocity has nothing to do with this problem. If they're both traveling at a constant velocity v, when the black ball is released from the plane as the plane travels, the red ball is still traveling at v horizontally, and the black ball continues to travel at v the whole time that it's falling because air resistance is negligible. In other words, the distance between these two objects as they fall is not going to change. So I have this drawn side by side so we can see the distances, but actually what would happen is if this was our plane and we drop the first ball from it, that first ball is going to be traveling in this direction horizontally at the same time. So 1 second later, this ball, if there's no air resistance, would be directly below the plane when the next ball is released. So they would be right on top of each other the whole time through their path of travel. So we're just going to neglect that horizontal displacement. We're only going to look at the vertical because we don't care about the horizontal displacement here. So let's look at the vertical. So we drop black ball. It drops for 1 second, and it travels some distance here. We'll just do the dotted line as our distance. It has a little bit of a velocity there. The red ball is still in the plane as we're traveling horizontally, and it hasn't been released yet. So 1 second later, the black ball has a gap, or the distance between the black ball and the red ball is this dotted line right here. And if you calculate your velocity at this point after the first second, velocity is equal to your acceleration times your time. Our initial velocity is 0. So we get 9.8 times 1 second. 1 second later, the black ball is traveling 9.8 meters per second. This should just be meters per second, not meters per second squared. That's our velocity. At that time, the red ball is released. And the red ball, let's just do 1 second later. 1 second later, the red ball will be in the same spot as the black ball was after 1 second. So we're going to be down here. We're going to be 9.8 meters per second. Again, it should be. And it's traveling downward. It's traveled the same distance the black ball did in the first second. But meanwhile, the black ball in that second of its path of travel, it was already going 9.8 meters per second. So it's going to travel a greater distance here than the red ball did in its first second of travel because it's going faster. And it's going 19.6 meters per second now after the second. So if we just compare the first displacement, the ball fell from here to here. That's your first distance between the two. The second distance between the two is going to be from here to here, and that distance is going to be greater because it's the distance that the black ball has traveled in the second second of flight. If we continue that downward, any object that accelerates, it gets greater and greater distances between the object as it falls, and you can see that as it represented here, but we also have it represented on our chart, and we're going all the way out of our chart now. But the black ball in the next second, because it's already going 19.6 meters per second, it's going to travel in greater distance. And if we look at the distance between this ball and the red ball, now the red ball's going to have the same path of travel as the black ball, just 1 second behind for that. That great distance is going to just continue to increase because, and here's why, at any point in time, this is the same point in time right here and here, the black ball always has a greater velocity than the red ball. It's accelerating at the same acceleration, but every second that passes, both of them increase by 9.8 meters per second, and it's always going to have a greater velocity. If it's always traveling faster than the red ball, it's always going to get a greater distance between the two. So that's your conceptual understanding for why that problem is A, it increases. Okay, let's look at our next one here. Astronauts are traveling on their planet. They wish to determine the value of acceleration due to gravity. They drop an object from the edge of a tall cliff, and this data is collected. And they want you to determine what's the acceleration of this object. The answer key gives you E being the correct answer, 52.8 meters per second squared. And here's what they tell you to do. For projectile with constant acceleration, they say use this equation. This is your kinematic equation. And graph y versus t squared. And if you graph y versus t squared, we're linearizing our data here. You're going to get an equation with the slope 1/2 a. And that slope, if you do a linear regression here, comes out to 26.4 meters per second squared. And then if you set that equal to 26.4 meters per second squared, your a here, you multiply by 2, and you get your answer here of 52.8. In other words, linearize your data. Well, that takes a lot of time. On the AP test, you might not have time for that. So I want to show you a method that takes a little bit less time that estimates an estimate of your acceleration. And it does a similar thing as your linear regression. We're just going to do it in steps by hand, so we don't have to type all that in. So here's your first thing you would want to do with your data. You would want to take your 2 time periods here, and I'm going to take both these and calculate the average velocity between these two. Well, velocity is v equals your change in displacement, x, over your change in time. And I have time here, and I have my displacement, my distance that's fallen. So I'm going to take my 4.2 minus 0.26. There's my change in x divided by my change in time, 0.4 minus 0.1. And I get this. This would be meters per second squared, or just meters per second. And this would be an average velocity for the time period 0.1 to 0.4. And you can assume as we're accelerating here, we are accelerating, we're just going to say that's our average velocity at this time period, 0.4. Do the same thing for the next time period, 0.7 to 0.1, or 1.0 seconds. And if you do that, you get 45 meters per second. And we're going to say that's our average velocity. Since we're accelerating, we're going to say that's at time 1. And that'll give us an equal distance between these two trials. So now we have an average velocity for this 0.4 seconds and the 1 second. If I have an average velocity for both of these, I can do this. I can say my change in velocity over my change in time is equal to my average acceleration. And we'll get an average acceleration for these two time values, the 0.4 and the 1, by taking the difference between our velocities and dividing it by our time. And the time between 1 and 0.4 is 0.6 seconds. So if we do that, it looks like this, 45, what we just calculated, minus 13, divided by the time period over which we did these averages, which is 0.6, and we get 53.1. And 53.1 would be your acceleration, your average acceleration, just a rough estimate here. And these would be quick calculations to do in your calculator. And 53.1, if you look at your choices, it's obvious which choice is closest to that. We just have to be in the ballpark region for that, and we would choose E for that. E is your correct answer. Oh, my pen's not working there. Okay, I hope that makes sense to you. That'll be easier than linearizing your data. You can just estimate your acceleration. Okay, here's your next missed one. In an experiment, an object is released from rest from the top of a building. Its speed v is measured as it reaches a point that is a distance d from the point of release. If this distance was doubled, what would the new speed be, assuming air resistance is negligible? This is a great problem because it has you relate variables to each other, and that's what I would expect to see on the AP test. Probably not one as straightforward as this, but you're going to have one that's going to be hard to Google. You'll find the answer to this online if you Googled it, but relating variables is a great way to see if you understand how to solve these problems. So here's our little diagram. We've got our ball, release it, it falls distance d, and it's got velocity v. And we want to know, if I add it to my diagram, what happens if we go to 2d? So we double this distance, we keep going down here. What's my velocity going to be there? Well, this is kinematics. So I want to know what's my kinematic relationship between a distance fallen and a velocity. How do I relate velocity to a distance fallen when I have an acceleration? And your acceleration would be g here. Well, that equation would be v final squared equals v initial squared plus 2 times a times delta y. And now I can relate my acceleration, my distance fallen, and my final velocity. Our initial velocity is 0, so that drops out of my equation. And if that drops out of your equation, you can solve this for your final velocity, and you get the square root of 2 times a times my displacement in the y. Well, I can plug in my values from my first case here. And if you plug in your values for your first case, you get this velocity down here is the equation square root 2 times g times d. I've just fallen the distance d. Well, my second velocity, we'll call it v2 now. v2 is going to be square root of 2 times g times, now my distance is 2d. And if you plug in 2d here and you solve this, you can bring that extra 2 out and rewrite it like this. That square root 2 from the d could come out, and we get square root 2 times the square root of 2 times g times d. That's what's left over. Well, that's just my initial velocity, v. So v2 is the square root 2 times v, and that's your correct answer. If you look at that problem again on AP Classroom, the correct answer you choose is square root 2 times v. Hope that helps for that problem. Our next problem, a ball is dropped from rest at time t equals 0. So our ball up here, from a height h on the top of a tower. At the same instant, a ball 2 is launched upward from the ground with initial velocity v0. If no air resistance is considered, at what time t will the two balls pass each other? So these two balls are going to pass each other at some point in time. They might pass each other at 2 points in time. Let's see, is that possible? Nope, they can't possibly pass each other at 2 points in time. So they'll just pass each other once. And how do we solve this one? Well, you want to use kinematics to represent what's going on here. Let's just treat one ball at a time. So our first ball, as it falls, if we want to figure out the distance that it travels, we're going to use this kinematic equation. The distance, we'll call it y1 for ball 1, is going to be 1/2 at squared. There's no initial velocity, so this is the only thing that we have in our equation. And for ball number 2, as it goes up, the distance it travels in the y direction is going to be, I have an initial velocity, v times t plus 1/2 at squared. Now I want you to note something I did here for my equations. I want these distances to both be positive. So I didn't define an axis, the same axis system for ball 1 and ball 2. You'll notice up here, I kept the 9.8 positive. So I'm going to get a positive displacement here for my y. Maybe it's 1 meter. And down here, I'm going to have a positive displacement for my y2 as well. The velocity is in the positive direction, and I put my acceleration in the negative direction. So this would give me a positive value for my y2 as it's going up on its path of travel. Well, we know that y1 and y2 have to add up to our distance h here. And if they add up to h, then the balls have met each other. y1 plus y2 adds up to our h. So I'm going to put my equation in here for y1. There it is. And my equation for y2, there it is. So y1 plus y2 equals h. And you'll notice here something cancels out. This simplifies greatly. The 1/2 9.8 t squared and the negative 1/2 9.8 t squared, those both cancel each other. And you're left with just v0 times t equals h. Well, that's pretty easy to solve for your time, and time equals h over v0. That's what the problem asks for. At what time will the two balls pass each other? And if you look at your question again, this is one of the answers for the multiple choice. Time equals h over v0. Last one here, a projectile is launched from the top of a 15-meter tall building at a speed of 25 meters per second at an angle of 50 degrees above the horizontal. So I'll do a little sketch here. Here's our 15 meters. I have some initial velocity here, 25 meters per second, and it's at an angle of 50 degrees above the horizontal. We want to know how far it travels horizontally. So it's going to take this path of travel. It's going to land on the ground here, and I want to know the distance from the ground as measured horizontally the ball traveled before it hit. For all of your projectile motion problems, you should be thinking, I need to break this down into two directions, the x direction and the y direction. They act independently of one another. So the x direction, we're going to have an initial velocity that's going to be the component of your velocity vector here. It would be the cosine of 50 times 25. And that remains constant throughout the whole path of travel. So at the end here, I'm going to have the same x value for my velocity. My y component here is going to change throughout the path of travel. It's accelerating downward with g, and that's what allows us to have a velocity of 0 up here. And we want to figure out, using our y component, how long does it take this ball to go all the way up to the top and then all the way back down this distance, 15 meters. So you'll start out with your y equation, and it's written here in the answer key for you. Your y displacement is equal to your initial y velocity times time plus 1/2 at squared. Well, we want to displace by negative 15 meters. We want to go downwards 15, so we hit the ground here. Our initial velocity is 25 times sine of 50. It's just that component vertically, times t plus 1/2, and we have a negative value here. It's in the opposite direction. We do have an axis system defined with up as positive. And if you solve this equation, you get a time of 4.59 seconds. That's how long it takes the ball to travel its whole path all the way up and down and hit the ground below at negative 15 meters. Well, then displacement, we just said that this x value for the velocity is constant through the whole problem. Well, if you have a time and a constant velocity, velocity times time gives you a displacement. and your velocity would be 25 times cosine of 50. That's a component of x times your 4.9, and you get 73.9. This is one of your choices on your answer key. I hope that helps for your Kinematics most missed questions. Yep, that's it for this one. Let me know if you have other questions that didn't get answered, and I'd be glad to help you out with those.